Hello, trig class. So we are going to do a little review of special right triangles and right triangle trigonometry, which you might know better as SOHCAHTOA. Looking at our pretest, it looks like these are all things we need to review, which is fine. So let's get started. Your first learning target is learning target 1E. I can find missing side lengths for 30, 60, 90 and 45, 45, 90 right triangles. All right. And to start, we're going to look at a triangle here that you just reviewed before. So first, think about what kind of a triangle is that in the photo. So that triangle, because all three sides are marked as congruent, is an equilateral triangle. And what do we know about equilateral triangles? Well, all the sides are congruent. Then that also means that all of the angles are congruent. So it's equilateral and what we call equiangular. If each of the angles are congruent, and I know that together three angles in a triangle add up to 180, well then each angle must be 60 degrees. Okay, so that is what I know so far. Let me just move this here. So when we're going to look at a 30, 60, 90 right triangle, it really stems from taking one of these equilateral equiangular triangles and cutting it in half. Okay, so I'm going to start at the very top of this triangle and I'm going to connect to the base of the triangle at a right angle, at a 90-degree angle. Okay, so what does that do to this triangle here? Well, it does a couple of things. First, because I'm connecting at a 90-degree angle, this is going to be a bisector, what we call a perpendicular bisector. It's an altitude as well. It came from the top of the triangle down to the base. And what we're doing here is we are splitting this triangle exactly in half. So I want each of those side lengths to be the same, which means that these side lengths over here need a different marking because they're now no longer the same size as the two on the bottom, right? They are double. Okay, so we chopped the base in half, and what we did to the top angle here is we also cut that in half. So when I have a 60-degree angle and I cut it into two, we now have two 30-degree angles. Okay, this line here is a perpendicular bisector, and it's also bisecting the angles. So bisecting just means to cut in half. Okay, so look what we just created. We created a 30, 60, 90 right triangle. Okay, if I ignore the other side of it, which is just the same triangle, we've created a 30, 60, 90 right triangle. And think about what we did here. Okay, so let's say that originally, these side lengths that we started with were, let's say they were 10 centimeters long, just for fun. Okay. Well, when I drew in the red altitude, what happened to the base of this triangle is that I cut it in half. So now each of these components is 5 centimeters each. All right. We only have two sides right now, and we're missing the third side. So if I wanted to find that, we could use our good old friend Pythagorean theorem, right? So let's set this up here with Pythagorean theorem. We would have, well, first, a squared plus b squared is equal to c squared. I'm going to make this really generic right now. So I'm going to use x for the small side, and if 5 is considered x, well, 10 is 2 times 5, so this side length would have to be represented with 2 times x, right? The hypotenuse is double the smallest side. So that tells me that a can be represented with x squared, and b squared is what we're trying to find. We don't know, but c can be represented with 2x, and I'm going to square that. So I have x squared plus b squared is equal to, well, 2x squared is 2x times 2x, so that's really 4x squared. And I want to solve for b, right? So I'm going to take away x squared. So b squared is equal to 3x squared. And then I'm going to take the square root of both sides, all right? So what happens when I take the square root of 3x squared? Well, let's think of this as the square root of 3 times the square root of x squared. What is the square root of x squared? If you recall, those are opposites, so they cancel each other out, so it's just x. It's the square root of 3 times x, which we can write more cleanly as x square roots of 3. Okay, so I'm going to get rid of this really quickly. When I look at my diagram here, this altitude is represented by x square roots of 3. Okay, so that means if this base were 5 centimeters, like we said, then the hypotenuse has to be double, which is 10 centimeters. And this altitude should be, well, x is 5, so 5 square roots of 3. All right. Let's see if that actually works when we use Pythagorean theorem with this. So if I use numbers instead of variables, we'd have 5 squared plus b squared is equal to 10 squared. 25 plus b squared is equal to 100. Take away 25, b squared is equal to 75, and take the square root. Okay, so this is where simplifying square roots has to come back into play. If this is something you might have a question about, maybe write that down for class and we can work a little bit more on that. But I want to think about what's the biggest perfect square that goes into 75? Well, it's 25. The square root of 75 is the square root of 25 times the square root of 3. And what's the square root of 25? It's 5. Ta-da! Look at that. We got the same value, but here I had to use Pythagorean theorem. Here, all I had to know was the value of x, okay? So I'm asking you the question, why is this helpful to know that the base, the smallest side is x, the hypotenuse is 2x, and the altitude is x squared roots of 3? Well, it's helpful, one, because it's faster, and in math we're always looking for a shortcut. And two, it's helpful because you can find all 3 sides of a triangle if you only know one of the sides. If we only knew x, or if we only knew 2x, or if we only knew x squared roots of 3, we could then find the other 2, whereas Pythagorean theorem requires you to know 2 different sides, okay? So let's generalize here. This is a good thing to really highlight in your notebook. If you're given a 30, 60, 90 right triangle, the side across from the 30-degree angle should be the smallest side, and that we're going to represent as x. Or actually, we'll represent it as a, just so we don't get confused later on. The hypotenuse, which is always across from 90 degrees, is always double the smallest side, so 2a. And then the side across from 60 is a square roots of 3, just like we said. So that's your generalization. That's what's going to help you when we're trying to actually put this into practice. Now let's talk about the other type of special right triangle. So let's investigate this here. First, I'm giving you a 4-sided shape where I've marked all 4 sides congruent. Hopefully we know what that's called. A square. And we know that if there's one right angle, there are 4 right angles. Okay, so we can see there that, well, as long as they're parallel, but anyway. If I'm telling you that these are parallel. So this is going to be a square, and part B, I want us to cut it in half and see what happens, all right? Just like we did with the triangle. We took an equilateral triangle and cut it in half. Now let's take a square and cut it in half. Well, over here, I still have a 90-degree angle. I have 2 sides that are the same length. Let's call both of those x just for fun. And then when I've cut the square in half, I've taken each of the right angles down here and I've split them in half. So if 90 degrees gets split in half, then each angle is 45 degrees. These are also going to be congruent because angles, angles here and here, those are alternate interior angles because these sides are parallel and this line is your transversal, okay? And same 45 and 45 here are also going to be congruent because the lines are parallel and those are alternate interior angles. But anyway, so if we know two sides of this triangle are x and x, we've created a 45, 45, 90 triangle. I want to know what is the hypotenuse, okay? So again, if you know two sides of your triangle, let's perform Pythagorean theorem. This time, both sides are the same, so a squared is going to become x squared, and b squared is going to become x squared, and c squared is what I'm solving for, or c is what I'm solving for. So x squared and x squared, where there's like an imaginary 1 in front of those, so if I combine them, I get 2x squared is equal to c squared. And then I want just c, so I'm going to take the square root, okay? So c is equal to the square root of 2 times the square root of x squared. We can break up radicals over multiplication. Just like we said before, the square root of x squared, those are opposites, so we end up with just x there. So this really simplifies to x square roots of 2. Okay, so let's think about it with some numbers and see if we get the same value. Let's prove that we did this correctly. So let's say x is 3. Both of these are length 3. So setting up Pythagorean theorem, 3 squared plus 3 squared has to equal c squared. And if we did it right, in theory, we should get 3 square roots of 2 as our final answer, okay, for c. So 3 squared plus 3 squared, well, 3 squared is 9. So 18 is equal to c squared. Take the square root. So c is equal to the square root of 18, which again I can break up over multiplication. Well, the square root of 18 is the same thing as the square root of 9 times the square root of 2. What is the square root of 9? Square root of 9 is 3. So we get 3 square roots of 2. Ta-da! Little fireworks should be going off. Very exciting, right? So what we've actually calculated with Pythagorean theorem is going to work for us every time. We're taking two smaller side lengths here. They're both the same, and if we know we have a 45, 45, 90 right triangle, the hypotenuse is one of those smaller side lengths times the square root of 2. So let's just generalize that down here. Again, something to highlight in your notes. So each side length I'll represent with a, just so we can keep it straight here. Sometimes x is in your problem a lot, so it's easier to use a different variable. And then we said that the hypotenuse is the shorter side, a, the leg, times the square root of 2, okay? So one of these special right triangles has the square root of 3 on a side, and the other has the square root of 2. The way I remember it is in a 30, 60, 90 right triangle, there's the number 30, we use the square root of 3, okay? In a 45, 45, 90 right triangle where two sides are the same, we use the square root of 2. That's how I help my brain remember it. But you can always, if you get confused, go back, draw the square, cut it in half, use Pythagorean theorem and see what you end up with, okay? And that will help you find the little rule. And then once we know that, we can use these shortcuts when we only know one side of the triangle. So let's do a little practice. So this first problem here, it's a 45, 90 right triangle. So we said both side lengths are congruent. So if the short leg 2 square roots of 2 is over here, then that makes b also 2 square roots of 2. And then we know from our little diagram there that if the two side lengths are the same, the hypotenuse is one of the side lengths, so 2 square roots of 2, multiplied by the square root of 2, right? This square root of 2 from here. So what do we get when we do that? Well, the square root of 2 times the square root of 2 is the square root of 4, and the square root of 4 is really 2. So we actually end up with 4 as the side of the hypotenuse. 4 is the length of A, right? So let's look at number 2. Here they gave me the hypotenuse. So I don't know why I circled that and not that. So they gave me the hypotenuse, and we know the hypotenuse is equal to A square roots of 2, and these are both side lengths A, all right? So if 4 is equal to A square roots of 2, right, that matches up, they're the same value, then I need to find just the value of A. So I need to divide by the square root of 2. So A is equal to 4 divided by the square root of 2. For now, I'm okay with you leaving your answer like this, but we should probably talk about rationalizing denominators, which you might have done at some point in your math career. But rationalizing a denominator means we don't want to leave a square root sign or a radical in the denominator. So in order to eliminate it, we're going to multiply by that divided by itself, okay? The reason that we do that is because square root of 2 divided by square root of 2 is equal to 1. And then watch when I multiply, we're going to go straight across here. 4 times the square root of 2 is 4 square roots of 2. The square root of 2 times the square root of 2 is the square root of 4. So that gives me 4 square roots of 2 over 2. And 4 divided by 2, these whole numbers here, I can actually divide. That just leaves me with 2. So 2 square roots of 2 is what that would actually come out to be. All right. Should make some sense because the problem we just did before that was the opposite direction, right? They gave us the side lengths that were 2 square roots of 2, which is what we just came up with here, which is the same as 4 divided by the square root of 2. And we ended up getting a hypotenuse of 4. Well, on number 2, we started with a hypotenuse of 4, okay? So they're just sort of reversing that process. Oops, sorry. So that's a really important point to note, though. And again, this is something, the rationalizing the denominator, if you're having trouble with that and you're like, what in the heck is Mrs. Levenseller doing? Please make sure you ask that question in class, okay? So number 3 here, we are given one of the side lengths. So this is like our A, which is 3 square roots of 2 over 2. This is another 45, 45, 90. So I know that this other shorter leg has to be the same size, 3 square roots of 2 over 2. To find the hypotenuse, we have to take the short leg, the leg here, and multiply it by the square root of 2. So we have to take 3 square roots of 2 over 2 and multiply it by the square root of 2. And I'm going to keep it in similar form, so I'm going to put it over 1. So 3 square roots of 2 times the square root of 2 is 3 square roots of 4, which is 3 times 2, which is 6. Okay? 2 times 1 on the bottom is just 2. 6 divided by 2 is 3. So even though this looked kind of scary before, this right here, the whole answer just came out to be 3. Okay, so the hypotenuse of that triangle is equal to 3. All right, let's look at a 30, 60, 90 right triangle. So just a refresher, 30, 60, 90, the shortest leg we'll call A, hypotenuse is double, side across from 60 is A times radical 3. So in this case, they have given us the hypotenuse. It's very large. And so that means that I want to try and find the shorter leg across from 30 first, right? Well, the relationship between these two is that the hypotenuse is double the short leg. So if the hypotenuse is 16, the short leg should be 8. And then this side across from 60, the longer leg, we call that, is just this short leg times the square root of 3. So if the short leg is 8, then x is 8 square roots of 3, right? Not too bad there. Let's look at another, and we'll keep that in view for a second. So here they've given me the short leg, the side across from 30. The hypotenuse we know is u. That has to be double the short leg, so 2 times 2, or 4. And then the side across from 60, the longer leg, has to be the short side, 2, times the square root of 3, or 2 square roots of 3. All right. Not too bad so far. Let's try one where they gave me the hypotenuse being 8 square roots of 5. Okay, so that I know is equivalent to the side that's double A, double the short leg. So if 8 square roots of 5 is equal to 2a, and I need to find a, I'm going to divide by 2. When you divide a radical, you only divide the whole numbers, not what's underneath the square root. So this would be 4 square roots of 5 is equal to a. So the side across from 30 has to be 4 square roots of 5. Now this, the longer leg, is going to be a, 4 square roots of 5, times the square root of 3. So let's do that. 4 square roots of 5 times the square root of 3. This is what's going to give me x. You can multiply the radicals together because they're similar, so we get 4 square roots of 15. And 15 can't be simplified, square root of 15, can't be simplified anymore, so that's all we need to do, okay? Let's do one more. Where to go? Okay, so 14, they're giving me the side across from 60, the longer leg, which if you recall is a square roots of 3. So if I'm trying to solve for a here, I need to divide by the square root of 3. So that means a is equal to 12 divided by the square root of 3. And again, I want to rationalize my denominator here. So I get 12 square roots of 3 over 3. I can divide the whole numbers, not the radicals. So that leaves me with 4 square roots of 3. And that would be the shorter leg of the leg across from 30 degrees. 4 square roots of 3. Now the hypotenuse, remember, is double A. So when we do that, it's 2 times 4 square roots of 3, which would be 8 square roots of 3. You're not multiplying the whole number with the radical, just the number in front of it. So that would be 8 square roots of 3. All right. So go ahead and give your 1.2 practice set a try.